In episode 58, titled Outliers in Context, Univariate versus Multivariate and Why They Break Assumptions, the main lesson is to treat outliers carefully because they can be truth or trash, and confusing the two is one of the fastest ways to sabotage both modeling and decision-making. Outliers attract attention because they are extreme, but extremeness alone does not tell you whether the value is a defect, a rare but valid case, or the exact behavior you are trying to detect. The exam cares because outlier handling affects metrics, interpretation, and fairness. And scenario questions often hinge on whether you recognize that an odd record might be a critical signal rather than noise. In real systems, outliers can represent errors in measurement, adversarial behavior, or genuinely rare operating modes, and each category demands a different response. If you build the habit of labeling outliers with process context, you stop reacting to magnitude and start reasoning about meaning. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A univariate outlier is an observation that is extreme on one variable alone, meaning it sits far from the bulk of values on a single feature. This is the kind of outlier most people think about first, like a response time that is orders of magnitude larger than typical, or a transaction amount that dwarfs the rest. Univariate outliers are relatively easy to spot because you can compare a value to percentiles, ranges, or expected bounds for that variable. The trap is that univariate extremeness can come from harmless causes, such as legitimate spikes, or from defects, such as unit conversion errors, and you cannot decide which without understanding how the value is generated. The exam often tests this by presenting an extreme value and asking what you do, and the correct answer usually involves investigation or contextual classification rather than automatic deletion. When you define univariate outliers clearly, you also establish that they are about one axis, which is only part of the outlier story in multivariate data. A multivariate outlier is unusual not because any single variable is extreme, but because the combination across many variables is uncommon or inconsistent with normal patterns. This kind of outlier can hide in plain sight because each individual value looks reasonable, but the joint configuration is rare, like a user with typical login count, typical device type, and typical location, yet an unusual sequence of actions and timing that rarely occurs together. Multivariate outliers matter because many real anomalies are pattern anomalies rather than magnitude anomalies, especially in security and fraud contexts where adversaries try to stay within normal ranges on each field. The exam may not use the phrase multivariate outlier, but it may describe an observation that does not match typical profile, which is a joint pattern clue. Recognizing multivariate outliers helps you avoid the false comfort of univariate screening because a dataset can look clean on each feature while still containing rare, meaningful combinations. When you narrate this, you are emphasizing that normality is often about structure, not about individual extremes. Leverage points are a specific kind of influential observation that can drag regression lines and distort fit, and understanding them is essential for interpreting linear models responsibly. Leverage is about being extreme in the predictor space, meaning the observation sits far from the typical range of inputs, giving it disproportionate influence on the fitted slope. An observation can have high leverage even if its outcome value is not extreme, and that is why leverage is dangerous. It can reshape the model's understanding of relationships for the majority of points. The result can be a fitted line that looks like it is compromising to satisfy a single unusual case, producing worse fit for the bulk of the data and misleading coefficient interpretations. The exam likes leverage because it explains why a model can behave oddly despite mostly reasonable data, and it reinforces why outliers break assumptions about stable relationships. When you describe leverage well, you are saying that some points are not just unusual, they are powerful enough to rewrite the model's story. Context is the only reliable way to label outliers, because the same extreme value can be an error in one system and a critical event in another. A value might be an error if it violates physical or logical bounds, such as a negative duration, an impossible timestamp order, or a code outside the allowed set. A value might be fraud or adversarial behavior if it matches known abuse patterns, such as rapid retries, strange combinations of geolocation and device fingerprints, or unusual sequences that align with attack playbooks. A value might be novelty if it reflects a new workflow, a new product behavior, or a new external condition that shifts the distribution, which matters because novelty often indicates drift rather than isolated noise. A value might be a rare class that is the primary objective, such as true incidents, failures, or exceptional outcomes. And in that case, the outliers are precisely what you need to preserve and model. The exam expects you to use scenario context to categorize outliers rather than to default to one rule, because outlier meaning is a process question, not a magnitude question. Once you label outliers, you can choose handling strategies that match the label and the modeling goals, and the exam often tests your ability to choose among remove, cap, transform, or model separately. Removal is appropriate when the outlier is clearly an error and cannot be corrected, because keeping it would inject false information and distort summaries and models. Capping, sometimes called Windsorizing, can be appropriate when extremes are plausible but overly influential, because it limits leverage while preserving the record's presence as a high case. Transformations like log scaling can reduce the dominance of extreme values in heavy-tailed variables while preserving ordering, making models more stable without pretending the extremes do not exist. Modeling separately can be appropriate when outliers represent a distinct regime, such as a high-value customer segment or a rare operational mode, where a separate model or segmented analysis captures different mechanisms. The key is that handling is not a cosmetic step. It changes the data's story, so it must be justified by purpose and context. A critical warning is to avoid deleting rare events when they are the main objective, because this is one of the most common and damaging mistakes in anomaly detection, fraud detection, and security analytics. If your goal is to detect rare incidents, then the incident cases will often look like outliers by definition, and removing them can eliminate the very signal you need to learn. Even capping can be harmful if it removes the distinguishing magnitude that separates true events from background activity, depending on how the event manifests. The exam often tests this by describing rare event objectives and offering remove outliers as an appealing but wrong answer, because it sounds like cleaning but actually destroys target evidence. The correct reasoning is to preserve rare events, validate them, and then choose models and metrics designed for imbalance and tail behavior. When you keep rare events, you accept that outliers are part of the phenomenon, not a defect to scrub away. When outliers are expected, robust summaries and robust losses help you avoid letting a small fraction of extreme values dominate your conclusions. Robust summaries like the median and interquartile range describe typical behavior without being hijacked by tail extremes, which is useful for reporting and for sanity checks. Robust loss functions reduce sensitivity to extreme errors, which can stabilize model training when occasional large deviations are normal and not necessarily informative. These approaches are not about ignoring extremes. They are about separating the story of the majority from the story of the tails so each can be handled appropriately. The exam cares because it tests whether you can adapt methods to data shape, and heavy tails are a common shape in operational and security contexts. If you insist on mean-based summaries and squared error loss in a heavy-tailed world, you will often get unstable parameters and misleading average narratives. Robust approaches are the disciplined response to expected extremes. Detecting multivariate outliers requires a different intuition than univariate screening, and distance and clustering reasoning provide a practical conceptual toolkit. Distance intuition says that observations far from the dense center of the data cloud are unusual, especially when the distance is computed in a way that respects feature scales and types. Clustering intuition says that typical observations form groups with tight cores, and points that do not belong to any core or that sit between clusters may represent anomalies. In mixed-type data, distance must be interpreted carefully because categorical and numeric features behave differently, but the conceptual idea remains. Multivariate outliers are points that do not fit the usual joint patterns. The exam may describe this as unusual combination of otherwise normal values, and the correct reasoning is to treat it as a multivariant anomaly rather than to dismiss it because no single field is extreme. When you practice this, you learn to look for pattern-breaking records, not just magnitude-breaking records. Outlier handling decisions should be documented because an outlier policy affects fairness and risk, and it can change who is treated as abnormal and how the system responds. If you cap values, you might reduce the model's sensitivity to certain high-activity users, which can change detection rates in ways that disproportionately affect a segment. If you remove records, you might remove uncommon but valid patterns that belong to smaller populations, effectively training the model to ignore them. If you model separately, you are explicitly acknowledging heterogeneity, which can improve fairness if done thoughtfully, but can also entrench assumptions if the segmentation is poorly chosen. The exam often treats this as governance and auditability because a defensible outlier policy must be consistent, explainable, and aligned with the decision context. Documentation also protects reproducibility because different teams can otherwise apply different rules and obtain conflicting results. When you narrate documentation, you are emphasizing that outlier policy is part of the model's behavior, not a hidden pre-processing trick. You should validate the impact of outlier handling by comparing performance and residual behavior because changes that feel sensible can still harm generalization or distort error patterns. If you remove errors, performance should improve, and residuals should become more stable. But if you remove valid rare events, performance on the cases you care about may collapse. If you cap extremes, training stability might improve, but you should confirm that the model still distinguishes important high-risk cases rather than flattening them into the crowd. Residual checks can reveal whether the model still shows systematic bias in regions influenced by previous outliers, indicating that the fix was insufficient or misapplied. The exam expects you to validate changes on held-out data because outlier handling can create overfitting if it is tuned to the quirks of one dataset snapshot. When you validate, you demonstrate that you treat outlier handling as a hypothesis-driven intervention, not as a reflex. Outliers can also be early signals of new behavior that may require new models, especially when they reflect novelty rather than isolated errors. If unusual patterns persist or grow, they may represent drift, new workflows, new user populations, or adversary adaptation, which means the outliers are becoming part of the system's new normal. Communicating this possibility is important because it frames outliers as operational intelligence, not merely as data cleanup problems. The exam may test this by describing a sudden increase in unusual cases and asking what it implies, and the correct reasoning can be that the system's behavior has changed and that monitoring and model updates may be needed. When you talk about new behavior, you also emphasize that models are not static. They must adapt when the data-generating process evolves. This is where outlier analysis connects directly to drift management and lifecycle planning. A useful anchor memory is, outlier meaning comes from process, not magnitude. Process refers to how data is generated, what values are plausible, what workflows create records, and what external factors influence behavior. Magnitude is only the symptom, and symptoms do not tell you the diagnosis without context. This anchor helps on the exam because it prevents you from choosing simplistic remove outliers answers when the scenario implies rare events, fraud, novelty, or measurement shifts. It also encourages you to ask what the outliers represent operationally, which leads to better decisions about whether to correct, preserve, segment, or transform. When you apply the anchor, you treat outliers as information that requires interpretation rather than as dirt that requires scrubbing. That is the mindset the exam wants to see, because it is the mindset that prevents damaging mistakes. To conclude episode 58, choose one outlier policy and justify it aloud, because justification reveals whether you are responding to purpose and process rather than to discomfort with extremes. A defensible policy is to transform heavy-tailed continuous features with a log-like transformation while preserving rare event records, because this reduces leverage and stabilizes modeling without deleting the cases that may be most important for risk detection. You would apply strict removal only to values that violate known bounds, such as impossible timestamps or negative durations, because those are clear defects rather than rare truths. You would document the thresholds and rationale, and you would validate that the transformation improves residual behavior and held-out performance while preserving sensitivity to truly risky cases. This policy is preferred when extremes are expected as part of the process, and the objective includes learning from rare events because it balances stability with fidelity. When you can justify an outlier policy in this way, you demonstrate exam-ready judgment. You preserve meaning, protect validity, and avoid letting a few extreme points dictate the model's story. Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.